Hello everyone, welcome back. So we are in week 12 and this is our last lecture, and in this lecture let us first revisit the Secant's formula, and for that if we consider the hinge boundary condition, if you recall, we have derived the expression for the second formula. So sigma max is equal to P by A within bracket 1 plus E y bar divided by R square sec L by twice R square root of P by EA. Right. So this equation we derived in the previous lecture. Now, if you recall, y bar is basically the distance of the extreme compression fiber from the neutral axis, right? E is the eccentricity and R is the radius of xylation. So we have E y bar divided by R square, and this is called eccentricity ratio. Right. Now today let us first consider an example and let us see how the stress changes with a introduction of small amount of eccentricity. And if you recall, we first started with Euler's buckling load, and in case of Euler's formula, that was purely based on some assumptions, and there we did not consider any eccentricity. And in reality, whenever we construct a column, it's very difficult to apply the compressive load at the center line of the column. Invariably some amount of eccentricity comes, and today in the first example we'll see how to use this second formula to evaluate the sigma max, and we'll see what is the impact of this eccentricity over the stress in the extreme compressive fiber. So this is our first example, and in fact we solved this problem earlier. The length of the column L is equal to 4.5 meter. Young's modulus E is equal to 2.1 into 10 to the power 5 Newton per millimeter square. Then sigma C for the material we have 500 Newton per millimeter square. The column is made of hollow circular cross section, and the outer diameter of the column is 200 millimeter, and the wall thickness is 25 millimeter. Now, for this column, our task is to find out sigma max given E is equal to, the eccentricity is equal to 10 millimeter. So let us consider a very small eccentricity, and we'll see the impact of this eccentricity on the compressive stress of the column. So we have hinge boundary conditions, or let me apply hinge using this notation. So we have point load P, but this P is having some eccentricity. So this is the centroidal axis, and we have load P is acting somewhere here. So this small eccentricity is 10 millimeter. Obviously the figure is not in scale if you compare with this one, where the outer diameter is 200 millimeter but we can follow the schematic diagram here. So we have the load with an eccentricity, right? Okay. So now let us first find out the moment of inertia and cross-sectional area. So moment of inertia I for this circular hollow cross-section is pi by 64 d to the power 4 minus small d, that is the inside diameter, to the power 4. So we have pi by 64, within bracket we have 0.2 to the power 4 minus small d is equal to 200 minus 2 into 25. So it is 150 millimeter. And the value here is 5.37 into 10 to the power minus 5 meter to the power 4. Let us also find out cross-sectional area, which is equal to pi by 4 within bracket capital D square minus small d square, right? So we have pi by 4, then 0.2 square minus 0.15 square. Now, if you find out this area, you get 0.01374 meters cube. Now, from capital I and capital A, we can find out R square, which is equal to I by A. And if you find out this, you get 3.9 into 10 to the power minus 3. So R is equal to 0.063 meter. Okay. Now we have to find out this sigma max for a load. So let us define the load. Load P is equal to 500 kilonewton. So this is the applied load, and for that we have to find out the maximum compressive stress, right? Okay. Now, if you recall the Secant's formula, we have sigma max is equal to P by A, which is sigma C, within bracket we have 1 plus E times Y bar divided by R square times sec L by twice R square root of P by EA. Okay, so sigma C is given, and that is 500 Newton per millimeter square. So this is 500. Then within bracket we have 1 plus E eccentricity, which is 10 millimeter. That means 0.01 times Y bar. So the capital D, the diameter of the outer circle, is 200 millimeter. So Y bar is 0.05 divided by R we have evaluated 0.063. So this is 0.063 whole square. And then we have sec within bracket L. L is 4.5 divided by 2 times 0.063 square root of, the load is 500 kilonewton. So we have 0.5 into 10 to the power 6 divided by E is 2.1 into 10 to the power 5, which is in Newton per millimeter square. So we know cross-sectional area. So if we write down this cross-sectional area in millimeter square, we have 13,744.46 millimeters. So that means here we have 13,744.46 and then right. So now we are going to solve it. So 500 times 1 plus 0.01 times 0.05 divided by 0.063 square. So we have 0.13 times sec within bracket, first one 4.5 divided by 2 divided by 0.063. So that is 35.71 times, if you evaluate the square root of this term, we will get 0.01. So now we can evaluate this term, sec of within bracket 35.71 into 0.01, and if you evaluate this quantity, we have 1.07. So what we have here is 500 times 1 plus 0.13 times 1.07. So this is 500 times 1 plus 0.14. That means you can see we have a eccentricity of E is equal to 10 millimeter, a very small amount of eccentricity, and for that our stress in the extreme fiber is increased by 14%, right? So 500 into 1.14, which is 570 Newton per millimeter square. Now we can see just by the introduction of a very small amount of eccentricity, how much stress is increased. From 500 it is now 570. So 70 Newton per millimeter square stress is increased, right? Because of eccentricity of 10 millimeter. Now we can easily imagine if we increase this eccentricity to 20 millimeter, obviously there will be a significant increase, almost 30% increase of stress, right? So that shows how to use second formula for a column which is having eccentric loading, right? Okay. Now today we are going to consider a different problem where we have a column but this column is also having a longitudinal load. For that, let us first consider a column. Say this is the column and it has hinge ends, right? And then we have a compressive load at the ends, and let us also identify the axis of the column. So this is X, and let us consider downward positive. So this is Y axis. Now the compressive loads are P and P at the ends. Now the length of the column is capital L and EI. And for that, the column bends like this, but in addition to the 2 point loads, at the ends we have point load W acting at the middle. So this distance is L by 2. Now for this column, we are going to derive the equation for this deformed shape, but this column is called a beam column. Okay. Now again what we do, we consider a cross section at a distance X. Now at this section we can find out what is m of X. For that we know there are support reactions because of the vertical load W. So we have two support reactions, one is here and another is here, and the support reactions are W by 2 and W by 2. So the moment at this section X, which is mx, is P times Y. This deformation here is Y. So P times Y plus we have W by 2 times X. So the governing equation is EI d2y dx2 is equal to minus Py minus W by 2 times X. So we can further simplify this. We have d2y dx2 plus lambda square y is equal to minus W by twice EI X. So we know lambda square is equal to P by EI, right? Now for this differential equation, we know the solution y of x is equal to C1 cos of lambda x plus C2 sine of lambda x. Then we have the solution for this Wx by twice EI on the right hand side, and that is Wx by twice P. You can easily cross verify the solution, which I leave it as an exercise for you. Now we have to apply boundary condition. So first boundary condition, is x equal to 0 offers y equal to 0. So if we apply that, we have C1 cos of lambda times 0 plus C2 sine of lambda times 0 minus W times 0 divided by twice P. This is equal to 0. Obviously, the outcome is C1 is equal to 0. Therefore, this term vanishes. So we have y of x is equal to C2 sine lambda x minus wx by twice p. So minus wx by twice p. Now for this problem, we also know at x equal to L by 2, the slope is 0. So if we find out y prime of x, we have C2 lambda cos of lambda x minus w by twice p. So at x equal to L by 2, y prime L by 2 is equal to C2 lambda cos of lambda L by 2 minus we have w by twice p, and this is equal to 0. So C2 is equal to w by twice p, then 1 by lambda sec lambda L by 2. Okay. So the equation of the deflected shape is y of x is equal to w by twice p times 1 by lambda sec lambda L by 2 times sine lambda x minus w x by twice p. Right. Now from this expression we can find out the maximum deflection which is at the middle. So at x equal to L by 2 we can find out the maximum deformation. So y max is equal to w by twice lambda p sec lambda L by 2 sine lambda L by 2 minus WL by 4p. Right. Now we can further simplify this expression. So y max is equal to, if you see, we have w by twice lambda p times sine lambda L by 2 divided by cos lambda L by 2. So we have tan lambda L by 2. Then this term minus WL by 4p. So minus WL by 4p. Okay, so we can also find out maximum moment, M max. For that, if we go back to the equation here, the maximum moment is at the middle. So we have P times Y max plus W by 2 times X, which is equal to L by 2, right? Okay. So M max is equal to P times Y max plus W L by 4. We have W by 2 times L by 2, so that is WL by 4. So we have P times, in place of Y max we can write W by twice lambda P tan lambda L by 2 minus WL by 4P plus WL by 4. So if we open the bracket, what we have, first term W by twice lambda tan lambda L by 2 minus P times WL by 4P. So P will get cancelled. So we have minus WL by 4 and then plus WL by 4. So they will also get cancelled, right? Okay. Now we can expand this tan in terms of infinite series. So tan theta is equal to theta plus theta cube by 3 plus other terms. So let us consider the first two terms, and in our case theta is equal to lambda L by 2, right? So let us use this approximation. So we have W by twice lambda within bracket, the first term is theta, that is lambda L by 2 plus theta cube, which is lambda L by 2 whole cube divided by 3. Right. Okay. So M max is equal to the first term, which is W by twice lambda times, if we open the bracket, first term is lambda L by 2. So we have lambda L by 2 plus W by twice lambda times the second term, which is lambda L by 2 whole cube divided by 3, right? Lambda L by 2 whole cube divided by 3. That means we have WL by 4, the first term, plus for this term we have W by twice lambda, and then here we have lambda cube L cube divided by 2 to the power 3, that is 8 times 3, so it is 24. So we can further simplify. So this lambda will give lambda square, and we know lambda square is equal to P by EI. So what we have here is WL by 4 plus we have W L cube. In place of lambda square we can write P divided by 48 EI. Okay, so that is the maximum moment at the middle of this beam column when we have the ends are simply supported and the compressive force is P, and we have W as the point load acting at the middle, right? Now, in place of W, which is a point load acting at the middle, we can actually have UDL, and then we can also derive the expression of maximum moment for the UDL if you have UDL, the support reactions will be the intensity of the UDL, say omega, times L, that is the total load, by 2. And accordingly, you can write down the expression for this mx. And then finally, you can solve and find out what is the expression for maximum moment acting at the middle. And in fact, you can also find out what is sigma max. Right? We have already solved one problem before this discussion, and then following that expression, you can also find out what is this expression for sigma max, and you can identify what is the contribution of bending and axial compression. Right? Okay. So, before we conclude today, let us once more revisit the second formula. And if you recall, sigma c, in the second formula, sigma c is P by A, right? And then sigma CR, that is critical buckling load, is M by Z. Z is the section modulus, which you can write in a different way. So M times Y bar divided by I, which is A times R square. Right. Now, if you have a column with eccentricity, so we can write down this M, which is P times E times Y bar divided by A times R square times sec lambda L by 2. So lambda is square root of P by EI times L by 2. So this expression we have already studied in the previous class, and sigma max is equal to P by A, which is sigma c. Within bracket we have 1 plus E times Y bar divided by A R square. It is actually R square because we have already taken P by A common. So E times Y bar by R square sec square root of P by EI times L by 2. You can recall that this term is called eccentricity ratio, right? Now, this sec term, sec of within bracket square root of P by EI times L by 2, this can be approximated. Let we have the compressive load is PC, and the buckling load we have PCR, that comes from Euler expression. So we can write this sec square root of P by EI times L by 2 approximately equal to 1.2 PCR E, that is Euler's critical load, divided by PCR E minus PC. Now, this means if we divide numerator and denominator with the cross section, we have 1.2 sigma CR E divided by sigma CR E minus sigma C. Right. Now, this second formula, let us modify with the expression of this sake of this first bracketed term, and let us see what happens. So we have sigma max is equal to sigma c, then within bracket 1 plus E y bar divided by r square, and then we have this sec of this first bracketed term that we can write approximately equal to 1.2 sigma CR E, that means compressive stress coming from Euler's critical load divided by sigma CR E minus sigma C. So now we can modify this expression. What we have here is sigma max divided by sigma C minus 1 is equal to E y bar divided by r square, and then here we have 1.2 sigma CR E divided by sigma CR E minus sigma C. So effectively what we can write is sigma max divided by sigma C minus 1 multiplied by sigma C E minus sigma C by sigma CR E. That also we can further simplify. So we have 1 minus sigma CR E divided by sigma C, which is equal to 1.2 E times y bar divided by r square. Now this expression is very useful because if you look at this expression, what we have sigma C, that is the compressive stress under direct compression, and then we have sigma CR E, that is coming from the Euler's buckling. Now if we know the Euler buckling load, which we have already derived, and if we know the cross section, the geometry, we can find out sigma CR E, right? Our task is to find out this sigma max, okay, because for design we need this sigma max. And if you look at the left hand side, so this term is dimensionless, this term is dimensionless, and on the right hand side we have this eccentricity ratio times 1.2. So if you have a design problem, we can easily find out sigma C from the compressive load and the cross-sectional area. We can also find out sigma CR E from the Euler buckling load, and we know eccentricity, we know y bar, which is the distance of the extreme compression fiber from the neutral axis, and from the cross-section we can also calculate what is r, that is the radius of gyration. So from this we can find out what is the eccentricity ratio, and moment we derive that using this expression, we can find out what is sigma max. So it is a very useful expression, and this equation is called Professor Perry's formula. This is very useful to find out the maximum compressive stress where we have contribution from direct compression as well as the buckling, right? And for a column with eccentric loading, right? This formula is used in different guidelines, and it is very useful to directly find out the sigma max. Okay. So now with these you have seen how to solve the buckling problem, and if you have different types of column, we can solve the deformed shape, and for different type of loading and boundary conditions we can completely solve the deformed pattern, and then maximum deformation, and then maximum bending moment. And then from those information, we can also find out the different components of compressive stress, and then finally we can also find out the combined maximum stress in the extreme fiber, right? So with that, let us close here, and this is the end of this course. If you have any doubt, do let us know through emails, or we will have open session. There also you can raise your questions and we will clear your doubts. Thank you very much.